You might remember Isaac from his talk on Ziegler, a very clever and clean way of adding Zig functions to an Elixir project. If you haven't seen that talk, I highly recommend you check it out, and in fact I also recommend you check out his YouTube channel where he dives into a lot of the details of how Elixir programs work. Today, Isaac comes to us with another great story, a story of sweat and blood. He fought a war against 44 other languages for us. Did he just survive, or was he able to also bring back glory with him? We all eagerly await his epic tale of implementing a drag race in Z. Isaac, the stream is yours.
Hey everyone. So this story is I believe the guy named Dave Plummer, who is an ex-Microsoft programmer, retired, has a tech channel, and he posed a challenge for himself initially, where he tried to code a drag race program in C, C++, and Python, just to see which would go faster. So what do we mean by drag race? A drag race means just do some sort of computational task as fast as possible, count how many times it does it, and and just benchmark how well you can how performant you can make the programming language. This is in the spirit of a drag race where you've got a car and you just want to go as fast as possible on land, and you're not trying to turn curves or do any sort of handling. It's just a straight line. What goes the fastest? So he then opened it up to other programming languages, and so now we have a huge competition between all sorts of different programming languages. They're going to be binned into different types, scripting programming languages, interpreted programming languages, and compiled programming languages. And being a compiled systems level programming language, Zig is in the running just fundamentally to be one of the fastest programming languages. So I won't compare any other programming languages. For that, you have to watch Dave's show. But I'll show you some of the optimizations that went into getting Zig to go as fast as possible. So first, the description of the problem. Oh, yeah. So these were the goals of why I decided to do it. I wanted to show off that Zig can be fast. I also really wanted to show off that Zig is easy to read, and show off the composability features of Zig, and of course, just have fun. So those are my three objectives. You know, and to some degree, we get a little bit of safety just because of the nature of Zig itself. But between speed and safety, I pick speed because that's the point of this. That's the point of this exercise. All right, so let's describe the problem. The problem is called solving the sieve of Eratosthenes, which is a way of figuring out. It's a very old way that dates the ancient Greek times of like finding which numbers are prime. I guess in the beginning it was finding whether or not a number was prime. We have much more efficient ways of doing that now, but as a side effect, it tells you all of the primes in a certain space of numbers. So I'm going to go over how that works so you can get a feel for how this algorithm works. So here's the basic form of the algorithm. The first step is we assert that one is not prime. So I'm going to take that off the list. Then we're going to look at our list of numbers, and which is a list of prime candidates. We're going to pick the lowest one. In this case, it's 2. And then we're going to smite all multiples of the candidate. So we're going to go down the list and knock all of these guys off. And then we repeat the process. We pick the next lowest prime candidate, and then we smite multiples of that candidate. Now, you might notice here that we have a situation where we may overlap with some numbers that have already been taken out. And that's just part of what you do. There's really no good way of optimizing that. Just like go ahead and just get rid of each value in the list. And eventually, you'll be left with only prime numbers, as you can see from the sort of demo here for the numbers between 1 and 20. Okay, so there are a couple of immediately obvious or you might call naive optimizations that you can do. These are mathematical optimizations, and there's one more mathematical optimization that we'll do later, but I'll talk about that in a bit. but these are kind of like not programming language dependent. You can do this in any programming language implementation. So I'm just going to go over with these with you. You should think of these as kind of like table stakes optimizations that everybody's going to do. So the first one is to ignore the number two. The array only represents the odd numbers, and as a sort of like a micro optimization, you can just consider the 0th slot to be the number two and just don't touch that. In which case, the transformation between your index and or between your number and your index is to divide by two and discard the remainder, and the reverse transformation is 2 times the index plus 1. And then, like I said here, except the index is 0, in which case we just consider that to be 2. The second optimization is to start sieving at p squared. So if I'm using the prime number 3, then I should not bother sieving until I get to the number 9. And why is that? Because if I have, or let's also talk about 5. So if I am doing 5, then the first number I should start out is 25. Now, why do I do that? Because there's only one prime factor before that, or there's 2 prime factors, 10 and 15. And 15 is already, we know that 15 has already been taken out because 3 was a previous prime. So the first prime that we have to start at is p squared, and that just cuts down your search considerably. Then the other one is to stop counting primes at square root of the size. So why do we stop there? Because the first multiple, like let's say we were going from 1 through 40, and the square root of 40 is something like 4 4 times something, and hold on, sorry, 5, 6. Sorry, so the square root of 40 is less than 7. So we can stop at 5. We don't have to go any further because the first number that we have to consider in 7 is 49, as from the previous rule. So we don't have to bother sieving. So that should hopefully those mathematical optimizations should make sense. All right, so let's go ahead and run this. I've got this all queued up. Let's do, all right. We're gonna run byte. So this is a naive run of the Zig Sieve program, where compiled with release fast, and I'll talk a little bit about that in a bit. It's just gonna go from one through a million. Which is the target size of the array that we're searching for, and just identify all of the primes, and then loop over again after having destroyed the sieve and start it over again. And we do that for over the course of 5 seconds and just see how many of these we can do. And so here is the result. We did it 5,600 times, and I've done it with 2 different data types, Booleans and U8s. And you can see that they're more or less the same. Actually, I find that typically U8 is faster, and for whatever reason on this run, Bool went faster. And I'm not entirely sure where that difference is, which is why I've included both implementations in the standard run. So the cool thing is that I have done it in more than one type, right? So I've used both Bools and U8s as a strategy, comp time selecting 2 different types to do this. And I'll go over exactly how that happens in another slide. Okay, so or maybe yeah, okay. So how do we verify that this run is correct? So we know how many primes there are in various slices of the integers, and so just the raw count. I know that from 0 to 1 through 1 million, there should be X number of primes. And in release safe, I check that number is correct. But of course, in release fast, we want to be fast, and checking to make sure that you're correct is not part of the criteria. So it just gets compile time eliminated if you're in release fast. This count of how many primes that you have is extremely sensitive to your initial conditions. If you get so much as one thing wrong, that number is very likely to be incorrect. So it's a pretty sound way of making sure that the code that you've written is accurate. And of course, the larger so if you're just checking 10, there's a good chance that it could be wrong even if it gets the right answer. So, if you look at the tests in the repository, you'll see that it gets tested at 10, 100, 1,000, 10,000, and so forth, every power of 10. And so as you progressively make your code better, you can check off more of those cases. It's actually really fantastic, and having inline tests and being able to write very easy to understand tests is huge point in favor of using Zig. Okay, so if you check out the repo, you'll see this basic layout. Build.zig is of course used to build the system, and it's pretty simple. Main.zig it contains the main program loop. Um, it has almost entirely just comp time stuff that is used for you to select out whether or not you want to run all, or if you just want to run sort of the focus set that I'm using for the program, both of which are useful for measuring relative rates and profiling in the course of developing. Then we have sieves, which is the actual implementation of the sieve. You'll see that there's going to be two different implementations that I have, and I'm going to go over the differences between those in a bit. There's runners.zig, which is if you kind of want to think of it as a runtime. So the challenge includes both single-threaded and multi-threaded. And so I have a runner that can do single-threaded and a runner that can do two different types of multi-threading. I'll talk about both of those in a bit. Alloc.zig contains a custom allocator that I wrote for this program. Wheel is an optimization that I will talk about a little bit later, and I want to keep that one for the last. And then test.zig is just a test suite that I use to make sure that all the components are working correctly. Okay. So let's talk about these four optimizations. So as I alluded to, I wrote two different sieves. One which has an array of bytes that get used, and one that has an array of bits that get used. So it's a bitmap. So and the reason for this is that 500,000 U8s is really big, right? And there's a lot of performance issues that can come about as a result. For example, having to allocate 500,000 bytes of memory in order to use it. So, can we do better? And yes, so we can store content at the bit level instead of the byte level. And one of the interesting things is that there's even a speed optimization that you can do, which is instead of like trying to index so one way you could try to find the next prime is you could, see that I'm sitting, remember I'm at this index, and then, index into each subsequent bit, and try and ascertain whether or not that is candidate prime or not. But the problem is that is a lot of like little sub accesses between and memory referencing and then masking, and that's a ton of operations, right? And they're dependent operations. So one speed optimization that we can do is we can scan 8 numbers at a time by checking to see if in the case of a U8, if all of the numbers in that small range are no longer candidates, and we just completely skip over that one index inside of the full array. So that's 8 at a time. Or if we are doing U64, it's 64 at a time. Or if we're doing U32, it's 32 at a time. So yeah, so those are the two benefits of doing bitmaps versus byte maps. So let's take a look at the speed. So for reference, it's going to rerun the bool. It's going to rerun the U8 case. And here's the bit sieve. So you can see that already it's like 50% faster. What you'll notice is that the U64 case is not quite as fast as the U8 case. And I think that has to do with the fact that the likelihood that you'll skip over one of these chunks. So this is a bit sieve that's backed by a U64 integer as your array of bits, as your chunked array of bits, as your chunk in the array of bits instead of a U8. And so the likelihood that all of your candidates in this are there are no candidates in a space of 64 subsequent odd numbers is lower than the likelihood that a span of 8 odd numbers doesn't have a prime inside of it. So you lose an advantage there. And I suspect that if the sieve size were to get bigger, so say 10 million, 100 million, the advantage between U8 and U64 will either close or possibly even flip. So I haven't tested that because it's not part of the competition explicitly. So if somebody wants to try that, we'll have a link to the source code in the show notes. Okay, so the next optimization is going multi-threaded. So I'll talk about two different forms of parallelism. So I call one Amdahl parallelism and the other one called Gustafsson parallelism because there's two different laws that are at operation. So Amdahl's law is that cooperation incurs a cost in their diminishing returns. And Gustafsson's law says that just spray your multiple cores with independent runs. And so Gustafsson's law is roughly linear. Of course, in no real system is it going to be completely perfectly linear because you'll still have some cooperation events, for example, locking memory or whatever. And operating system will play weird things with multiple cores that you have no control over as the systems programmer. And so the Dave Plummer's original talk does everything with embarrassing parallelism. So what they do is they just run the sieve program and they just spawn threads and then run the sieve program on each of those threads, and at the end they just add together the results and say this is how many times we're able to run it. I also wanted to just play around with Zig concurrency and do one where instead of just doing the naive sort of parallelism, see if I can't write something where they cooperate. And so in the case of the Amdahl's law parallelism, it only works on one sieve all cores only work at one sieve at a time. And what happens is that the main loop first figures out what factor I'm going to work on, and then it leaves behind, here's the next factor to be worked on, and the other cores try to pick that job artifact up, and then leave behind another, hey, here's the next one, and then the next thread comes in and does that again. And the process of picking the next job is locked. So there's a little bit of there's cooperative gating between those events, but everything else is free. So these threads can go and just write to memory willy-nilly, and because the algorithm itself is subtractive, you don't really need to enforce any sort of memory safety, except for preventing use after free when all of the jobs have finished. But that should naturally happen if there are no jobs. There are no jobs on sort of the queue to be, or not even a queue, in the one slot to be run. So yeah, perhaps unsurprisingly, the Amdahl's law so we're going to run the multi-threaded version. So as it'll again rerun the sieve comparison with U8. There is a speed up if you use Amdahl's law. It's almost 2x, which is I think quite good. But even though my system has 8 cores, but you see a much more pronounced improvement when you're doing the massively parallel one. Now, There is an even more of an improvement with the Bitsiv version, and I think that that has to do with the fact that there's less memory going on, or there's less memory access needed because there's everything is scrunched down by a factor of 8. Um, and yeah, you can't do a Bitsy version of Amdal because you don't want conflicting writes onto. Well, you could if you made each memory U8 temporarily atomic, but that's really inefficient, so I didn't bother. Okay, so the special allocator. So you know, in the base case, we've got already 7,000 allocation events. So let's not take trips to the kernel. So I wanted to write a really efficient custom slab-ish allocator. In sort of in release fast, runs are backed with page allocator, but in tests they're backed by testing allocator. So we know there are no memory leaks, and I think that's one of the nice safety pluses. And also there are no use after freeze or there's unlikely to be any use after freeze because with testing allocator, use after freeze will typically cause a seg fault. But not always. So I'm fairly confident there are no memory leaks and there's no memory safety issues with the allocator that I've written. So let's compare the two and see whether or not. Oh, right. So by a slabish allocator, how does this work? So when you request a page or a set of pages of memory, it keeps a list of all of the memory units that it's already allocated and have since freed. And if it can find one that has the same size, it simply promotes that to used. And then when it's done, it will demote that pointer back to freed. And if there are no free ones available, then it takes a trip to page allocator and then sends that up. So yeah, it's pretty simple. This is very much a stripped down version of what something like malloc does under the hood. Malloc will try to not give you trips to the kernel, but there is a lot more logic that malloc does because it's not quite as specialized. And one of the great things about Zig is that it gives you the freedom to really create an allocator that is tuned to your use case. And I think that's really powerful. And in this case, it's something you might want to do. So let's take a look at comparing those guys. So again, it will run a few of these different scenarios. And you'll see that in one case, I'll have the base, and in the other case, I'll have it using malloc. So for the single-threaded sieve, it's a wash. For the parallel sieve, the not having a malloc is a real benefit. And so you can see that here. And I think that there's possibly even, and I think for the Bitsieve U8, it's a wash. But I think that there's one more optimization that I can do, which is to use thread local variables instead of locking, and that might push this to be even better. Okay. Last thing to talk about is the wheel. This is really cool, and I think that it really shows off some of what really makes Zig awesome. So here in Zigland, we really love comp time, right? And if you look at the code, a lot of the stuff in the main Zig is comp time because I just build these types for these composite types where I'm plugging in a bit sieve into parallel, but also I can plug in a byte sieve into parallel or do it single threaded or doing Hamdal. All those things are composable because at comp time it builds out a unique type for each type of run that it's going to happen. So why not pre-compute some of the primes beforehand and just go for it? So you're going to get. So what you can do is you can just run your sieve over some short span, and then and then just you know, roll that out of your memory. Um, and that'll be a recurrence relationship. And so you just roll that out more than once until you hit 1 million, and then that'll save you some time because you just don't have to do a bunch of the work going up front. And especially, you'll notice that this makes a huge difference with the bit sieve because of the whole skipping process, right? If you the Some of the more expensive runs are the runs where it can't skip as many as, especially when you're doing 3, 5, 7. It's not going to be able to skip any of the bytes. But like once you start pre-computing, you already start dropping out bytes that it has to bother to check. Um, so it really makes a huge difference for some of these bit sieves, as you'll see. So what I'm going to do is, this is the only language comparison you'll get. I'm going to show you how it's done in C, and then I'm going to show you how it's done in Zig. So in C, there are these special C files, and what you can see is they've manually dropped in a bunch of this is actually delta encoding. So it says how many steps exist between this prime and the next prime. So there's two problems with that. One, you have to do a seek and then write, and a seek and a write. Whereas with a memory drop, you can just roll it over and possibly use an optimized memory move operation. And you just have to how do we know that this is right? I mean, obviously we're checking our answer, but say this were a 4 instead, right? That would cause a problem, and it's basically impossible to review. By contrast, if you look at the code in wheel.zig, here's what we do. I make a wheel type that is a function of the count, and then how many, and this count is how many of the primes I'm going to use. So I just preceded the first 1, 2, 3, 4, 5. We never use more than 5 primes, anyways. And what it does is it actually goes through and runs the sieve program using a comp time array, basically, and then it runs it just for the set of the primes that we care about, and then it saves the buffer into this template. And then when we run one of the sieves, if it's been instrumented with one of the wheels during the init process, it'll just take that template and copy it out. So this is using comp time to use the exact same algorithm that we're using for the rest of the program in the main program to pre-generate our seeds, which I think is exactly what you want to do to have sort of like a consistent view of all of your code. One little thing that you should know is that Zig puts a cap on how many computational events you can have, or how many evaluation branches you can have at comp time. And so you kind of have to do this little trick here to get it to actually run the entire sieve. Okay, so a couple of more implementation details. Obviously I have to do things. I have to create a different memory layout depending on whether it's a byte sieve or a bit sieve. And the key to understanding that is that I have to do this thing called compression. And indeed, all of these recurrences, because they're product of odd numbers, they won't align to a factor of 8. So what I wind up doing is I wind up dropping in 8 copies of the recurrence, and if you know a little bit of basic college algebra, if you multiply an odd number by 8, you will always get something that's divisible by 8. And so this lets you, by making 8 copies of the of the bit mapped recurrence, you can get something that you can actually fit into 8 bytes. Or it's 8 bits, which is 1 byte. And the last thing is, just be careful. Comp time arrays are a little bit tricky. You have to remember that this is going to get placed in a slot in memory somewhere in your program, and so you have to be careful about treating arrays which are not pointers. They're actually like a block of memory versus what is a pointer to an array, which is a pointer. So just keeping in mind that doing those sorts of manipulations, that's one place where I have to say the reading of the code can get a little bit tricky. What's an array? What's a pointer to an array? And how to like handle those correctly. Okay, so let's run it. So these are our reference runs here. And what you'll see is
Isaac, make sure to add some new lines if you can.
Because am I coming up against my...
Yep.
Yeah, let's do this. How's that? So the first number is how many... So the second one is the size of the recurrence and how many primes exist in there. And the first number is how many primes exist inside of that recurrence. And you can see just how tremendously beneficial this is to the number of times we can run it. I mean, already here you're seeing, a several factor jump in the speed. Okay, so last thing I want to talk about is that there is on Thursday, Specs guy and I took a look at this using Tracy, which was exciting. I'd never done anything to like that before. And we were kind of looking at the performance, just trying to see if we could squeak out any last bit of performance. And I think we're pretty close to being sure that getting any extra is going to be difficult. I think maybe the allocation one might help. But yeah, there was even a case where we thought we could optimize something by removing memory access. And it turned out that probably it's the memory that we were accessing was probably an L1 cache because it's being accessed so quickly. And the latency, even though each iteration had a longer latency, because the CPU is pipelining everything, and can reorder the operations of the actual machine instructions that are going in, because the memory access that we were doing reduced one level of dependency, we could dispatch one operation, one sort of prime search operation every 2 cycles instead of every 3 cycles. And so what we thought would be an optimization turned out to be a pessimization. And sort of this very old school way of having a lookup table where you've got a memory access wound up being a factor of, wound up being 30% slower. So, I think to me that what was learning for me was that sometimes just having really sloppy old school code might actually be okay, and trying to overthink the problem can wind up, especially if you don't have real data real profiling data to back up your supposition. You could just be poking in the dark, trying to find something that's based off of a guess when the CPU, which knows better, might do something you don't expect and wind up pessimizing your code. So again, having this sort of pluggable system where building out something where I can do comparisons like this super easily is because of the composability of Zig types, and the fact that they're just hey, I can just write a function that generates a type at comp time, really makes a huge difference. So yeah, Um, Look at the speed up. This is almost an eightfold, sevenfold speed up from the single speed naive implementation to the parallelized on 8 cores, right? Okay, so that's all I got. Special thanks to Mandijan, who got this all started. I mean, it looks considerably different from what he has, but like I bootstrapped all of my code off of his and got into the challenge because of his solution. And I want to thank Specs Guy for running Tracy with me. And yeah, I'll take questions.
Awesome. So if anybody has questions, please, that's the time to write them down. So Isaac, I've already asked you about this, so I'll have to figure out another starting question. Um, I don't know. So, I think maybe I have one. So if we were to have one day a first Zig conference in the United States, where would you want it to be?
Well, obviously, I wanted to be in the city where I am. Uh, it turns out that Specs Guy is like a couple of miles away from me.
Did
So
he
there's at
like
least
come
two of us in
over?
the city. No, no, we did it over virtually, but it's really funny. Like,
Mhm. So okay, so we can say the state, right? That shouldn't be a problem.
yeah,
So
yeah,
somewhere in
Texas.
Texas. Okay.
Come to Texas. I mean, I guess it's public knowledge because of the website. Specs Guy's on there. We're in Austin. Come to Austin,
All
everyone.
right. Um. Okay, so that was cool. How was it like doing the all the improvements? Like did you feel like you were stuck? Did you always find something else to work on and test your hypotheses? Like how was the emotional experience of doing this work?
It was pretty straightforward, but always like, there were a lot of times when I did something that I thought was an optimization and then it wasn't, and or made it worse. And that's always a little bit disappointing because you put considerable amounts of effort into like, oh, how do I rewrite this? I will say that like for a while, I had accidentally gotten overconfident because I had double counted the number of runs, right? Like, so there was a point where I'd switched over from counting, having the count be done by incrementing a pointer to the count, and then originally it was just as sort of the after each run dispatch inside of a while loop, and I needed to do the pointer one to get the multi-threaded implementations to increment the runs, right? And so I was overcounting,
Hmm.
and so but thankfully I caught that and it's upstream or it's PR'd into the drag race. So hopefully, but it made me like I got to be really careful that like everything that I'm doing is correct.
Yeah. So let's see what people are saying. So people, people just want to know who's gonna win. So so Andrews is saying, so are we gonna win the drag race? Rat Factor is asking, are you feeling good about Zig's chances in Dave's competition?
I'm feeling pretty good.
Mm,
I mean, I can't say for sure because people can still, PR updates. Just having looked at the Tracy makes me feel really good.
hmm.
Um, you know, we really like looked. We really tried. And when your hot loop is dispatching one per 2 clock cycles, that's gonna be hard to beat.
Hmm.
Now, would the pessimization that we tried out be better for some architectures where um, where some architectures where the system like doesn't do that sort of thing? Yeah, probably. And if I wanted to, I could probably make that be some sort of compiler switch to do one version versus the other. But
Yeah.
I there's so many ways that sort of like self-management of how many options I want to have in the in sort of the compile time options has kind of like been a thing, right?
Yeah.
Um, yeah. Okay. So if you want to know whether or not we're going to win, what I suggest doing is that the Dave Plummer's um, uh, GitHub repo, which Lars will put in the links, um, has a Docker container that you can, or a Docker build script that you can run, which will run a comparison between the different programming languages.
Hmm. So I saw a couple of
But
interesting
I actually haven't
comments.
done that because I
Oh,
don't run Docker.
you're a Docker agnostic.
I just don't like a I don't want Docker D to run on my machine. So I use Podman. I use Docker containers with Podman.
Mm. Okay, so
I'm one of those guys.
I think there was an interesting type of comment that I remember seeing a couple of times because we know one thing that in a recent video Dave posted, like somebody said, of course C, C++, or assembly are gonna win. And they replied, oh no, you know what? Turns out that right now neither of these languages is in the lead. And people then immediately replied, well, I mean, of course it's impossible for another language to win. It's assembly. What could possibly win over assembly? And I think that points out a very interesting point about engineering. Do you want to give a comment on this, or do you want me to do it?
Yeah, I mean, there's just stuff you're not going to do in assembly, right? I think that like writing the fastest thing that I can run on this on my machine, which is like the um, eight threads, plus the bit sieve plus uh, plus the special bit sieve optimization that I have. I think that you would not want to write that in assembler. I mean, I'm not, obviously you can because, trivial solution, compile it in Zig, pull the Godbolt, pull copy paste from Godbolt if you want, and then submit that as an assembler solution, right? You could do that, right? But I think that's like not really the point, right?
Yeah.
Um, yeah, there's a lot of question marks. Fortran can be really fast at this sort of stuff because it has fewer jumps sometimes. Zig is pretty good at aggressively inlining, so I don't think that Fortran can will beat it. But do I know enough about Fortran to say that for sure?
Hmm.
No, right?
Right. At the end of the day, it turns out that it also matters whether there is somebody willing to do the job, right? Yes, in theory, somebody could write an assembly version that can do at the very least everything that what the Zig version does. But if nobody does it, then it's not there. And the abstract point of saying, of course, assembly is the fastest language or whatever, it's kind of moot.
Right. And I mean, you can see all of the different optimizations that I've applied. And really that was easy to try everything and then try a new thing, try a new thing and then just kind of bootstrap it back into the other parts of framework. Everything was just really interchangeable parts. And we do it without vtables. So
Yeah, that's interesting. Oh, so this is then the flip side of the coin is okay. So assembly technically the fastest, or although also when it comes to multiple architectures, like there's no metaprogramming, you would have, I guess, to provide multiple solutions, and in practice is a mess. So okay, but what about the opposite side of the spectrum? So we are here praising the power of metaprogramming and generics, basically, and generics plus plus, so templates. So why is C++ not winning? I mean, are they still compiling? Is that why?
I don't know. I mean, I think that like to do this sort of metaprogramming stuff in C++, you're typically using objects that have virtual tables, right? And
Mm,
that's already one level of indirection too slow. Um, Maybe Rust has a better chance because everything is done with macros instead. Um,
yeah.
but macros are kind of clunky, and there's a lot of stuff that we're doing that you can't do with macros so easily.
Mhm. I think
Um,
that also for C++, some people, like, I'm thinking probably Snectron, if he was here, he would probably say, well, no, I would know how to implement this stuff with like 3-page longer template expressions. So I'm guessing, though, that they also somehow touch upon some kind of limit there, too.
yeah, yeah. I mean, I'm done with templates. If I never have to use templates again, I'll be a happy camper.
Yeah, that was actually also my experience. I once was using the fastest Fourier transform in the West, right? And yeah, got a nice template error. It was like 3 screens of my terminal long, and I said, you know what? I think I'm good. Goodbye.
I mean, let's not, sometimes Zig types when they
Yeah, that's
when
true.
they vomit on air, they can get kind of long too. So,
Yeah. We need to
but
find out a way of like containing this stuff, because I think I genuinely remember still my immediate reaction of complete refusal of wanting to deal with a giant template error. We need to find a way of dealing
well,
with that.
I mean, I think the other thing is that it's really not the worst in Zig because you are encouraged to like write tests and stuff.
Yeah.
And, worst case scenario, maybe we might need to figure out how to like run a single test inside of a file. That would be awesome. But like, you can at the very least take your test, like, drop it into another file, isolate it, run the test on that one file, and then really kind of like hone in on what the problem is.
Hmm.
Um, so, that one piece of ergonomics like really I think helps out a lot. Like
Yeah.
I don't think I don't like, despite the fact that we have maybe three levels um three levels of meta programming through Zig's type system going on in this program. I never ran into a situation. I think maybe once I ran into a situation where the type got more than like 2 or 3 lines long.
Hmm. Andrew is suggesting to use test filter. Are you aware of that flag?
No, I'm not.
So you can use that. You can basically run zig test dash dash test filter, and then you provide the test name. But Andrew, a file name colon line option, maybe, I don't know.
Yeah, that would be awesome because or yeah, so when I code in Elixir, which has like, robust testing, I
Hmm.
get, this is the line, and this is the file and line that failed in the test result, um uh output. And I can just copy paste that and just run test on that one thing, and that's a huge lifesaver.
Hmm. Oh, so the idea of having like a quick continuation from, okay, so I'm running all the tests. This is the one that failed. Let me give me a quick way of running that test, which could be a solution that also is just in the, like, maybe the error message could even suggest that command for you. That would be probably.
Yeah,
Mhm.
exactly.
That's cool. Okay, so let's see. Oh, there's a question that I was missing from Salau TV. Let's see. I saw that the code was marked unfaithful at some point. Why was that, and what did you do to fix it?
Right. So, two problems. I'm glad I had to fix it because that also got me to fix the double counting problem. Uh, Unfaithful. So one was that I was only clearing out um the sev between runs, and so they want you to actually go through the process of an init and a dinit. Uh, and so in practice, that winds up being just shuffling things in an array. or in a slice. So not the worst. They also didn't like that my initial uh, implementation of the custom allocator um, used scratchpad memory that was allocated in .bss. So it was compile time. It's load time allocated. So when the program gets loaded, it gets, it reserves certain amount of memory to go.
Mm-hmm.
Um, and I mean, I thought about that and I was like, that's not gonna make a difference because we're not measuring end to end, including the command line, right? We're not doing a Unix, we're not doing the time command to measure this. So I was like, it's an unnecessary optimization. And so, yep, so I got rid of it.
I see. So just for clarity for the other people that might not be aware what unfaithful means, the idea is that everybody's re-implementing in other languages something similar to the original solution by Dave, right? And unfaithful, I'm guessing, is a re-implementation that it's a bit too far, right? It changes some details that you're not supposed to change.
Yeah, so originally unfaithful was supposed to mean just the algorithm, the mathematical algorithm. So maybe if you did something like um, scan one page only, and then move on to the next page, and somehow cache like the primes that you've done. I think that would have been that was kind of one of the original examples of what constitutes unfaithful. Or if you use a completely different algorithm altogether, that's unfaithful.
Yeah.
But they started expanding it to like, okay, these are some other things that we want you to do.
Mm-hmm. Understood.
Just fine.
Okay, I think we are good. Thank you, Andrew, also for pointing it out. I think that's it. Isaac, is there anything else you want to say before we call it a day?
No, it's been great. Thanks for hosting me again. And I'll see you guys around. Maybe I'll come down to Texas.
Ooh, nice. Well, then, thank you very much, and see you on the next talk, Isaac. Okay, so we are at the end of the show, and